The heat death, often called the Big Freeze, is one of the most prominent theories describing the eventual fate of the universe. It proposes that the cosmos will gradually move toward a state of maximum entropy, where all energy becomes uniformly distributed and no meaningful processes can occur. Instead of ending in a sudden collapse or violent transformation, the universe slowly fades into darkness as temperatures drop and activity diminishes. This model carries significant weight in modern cosmology because it closely follows the laws of thermodynamics and aligns with current observations of accelerated cosmic expansion. The origins of the idea date back to the 19th century, when physicists like Lord Kelvin and Hermann von Helmholtz explored the long-term implications of thermodynamic entropy. As scientific understanding of the universe expanded in the 20th century, researchers connected these principles with the cosmic expansion revealed by Edwin Hubble and later, with the discovery of dark energy. Over the decades, the heat death scenario became a central component of cosmological discussions, evolving alongside advancements in both physics and astronomy. The mechanism behind heat death is gradual but relentless. As the universe continues to expand, galaxies drift farther apart, and matter becomes increasingly scattered. Stars exhaust their fuel and burn out, leaving behind remnants that eventually cool to darkness. Black holes themselves evaporate through Hawking radiation over unimaginable timescales, leaving only diffuse particles and fading energy. With entropy increasing indefinitely, the universe becomes unable to sustain any physical interaction or structure. In the final stages of this process, the cosmos reaches a cold, empty state approaching absolute zero, where nothing new can form and nothing meaningful can occur. Heat death remains one of the most widely supported end-of-universe theories today, backed by strong evidence for continued cosmic expansion and the dominance of dark energy. The Big Rip is a dramatic cosmological theory proposing that the universe will ultimately be torn apart by the relentless acceleration of its expansion. It suggests that dark energy, the mysterious force driving the universe to expand faster over time, could grow in strength rather than remain constant. If this occurs, the expansion would eventually overwhelm every form of matter and every binding force, from galaxy clusters down to atoms themselves. The theory is significant because it offers one of the most extreme possible endings to the cosmos, illustrating how sensitive the universe's fate is to the true nature of dark energy. The concept began gaining attention in the early 2000s when cosmologists considered what would happen if dark energy behaved differently from the cosmological constant proposed by Einstein. Researchers like Robert Caldwell and his colleagues introduced the idea of phantom energy, a hypothetical form of dark energy with properties that cause the expansion of the universe to accelerate without limit. As observations continue to show rapid expansion, the Big Rip became a notable alternative to more traditional models like heat death or the Big Crunch. The mechanism behind the Big Rip centers on the growing dominance of dark energy. As its influence strengthens, gravitational structures weaken. First, galaxy clusters drift apart. Next, individual galaxies become unbound. Stars separate from their galaxies, solar systems lose stability, and planets are flung into isolation. In the final stages, the expansion becomes so violent that molecules, atoms, and even subatomic particles are pulled apart as space-time itself stretches beyond the ability of forces to hold matter together. If the Big Rip occurs, the universe ends in complete disintegration, leaving no structures, particles, or space-time continuity. While the theory remains speculative, it is considered plausible within models where dark energy increases over time. Most current observations favor a stable form of dark energy, making the Big Rip less likely, but it remains an important scenario in the broader study of cosmic destiny. Now, before we continue, let's talk about our sponsor. This video is sponsored by Manta Sleep, the brand on a mission to empower better sleep anywhere, anytime. If you've ever struggled with light ruining your rest, their masks are a game changer. Manta Sleep masks are fully adjustable, designed to fit any face comfortably, and have this incredibly premium feel that blocks out 100% of light, so you get real deep sleep. Whether you're at home, on a plane, or just taking a power nap between projects, their masks make sleep feel effortless. So if you want to experience better rest, visit mantasleep.com and use my code SciMind for 10% off your order. Now back to the video. The Big Crunch is a cosmological theory proposing that the universe's expansion will eventually reverse. causing all matter and energy to collapse back into an extremely dense and hot state. Instead of fading into cold emptiness or tearing apart, the universe would retrace its steps toward a final moment, reminiscent of the conditions that began the Big Bang. This concept is significant because it presents a cyclical or symmetric counterpart to the universe's origin, offering a dramatic and orderly conclusion rooted in gravitational dominance rather than eternal expansion. The idea originated in the early 20th century as scientists first explored the implications of general relativity. When Edwin Hubble discovered the expansion of the universe, theorists began debating whether gravity might someday halt this outward motion. Researchers such as Richard Tolman later investigated models in which the universe oscillates between expansion and collapse, giving the Big Crunch a foundational place in classical cosmology. For decades, it stood as one of the leading explanations for the universe's long-term evolution. The mechanism of the Big Crunch depends on gravity eventually overpowering expansion. If the total mass and energy of the universe were high enough, expansion would slow, stop, and reverse. Galaxies would begin moving closer together, merging as space contracts. Over immense timescales, temperatures and densities would rise as the universe shrinks. Structures would break down, stars would collide, and cosmic background radiation would intensify as all matter compresses into an increasingly smaller volume until everything converges into a final, superheated singular state. The ultimate outcome is a universe that ends by collapsing into extreme density rather than drifting into emptiness. While once widely considered plausible, the discovery of accelerating expansion and dark energy has made the Big Crunch less favored today. However, it remains an important theoretical model, especially in discussions of cyclic cosmology and alternative gravitational scenarios. The Big Bounce is a cosmological theory suggesting that the universe did not begin with a singular Big Bang, nor will it end in a final collapse or dissolution. Instead, it proposes that the universe undergoes an endless cycle of contraction and expansion. According to this view, the current expanding universe emerged from the collapse of a previous one, and when this cycle concludes, the cosmos will once again contract before bouncing into a new phase of expansion. This model is significant because it avoids the notion of a true beginning or end, offering a universe that is eternally self-renewing and eliminating the singularity problem associated with the classical Big Bang. The concept has roots in early 20th century cosmology but grew more refined in the mid to late 20th century, with the work of scientists like Richard Tolman, who explored oscillating universes. Later, advances in quantum gravity and loop quantum cosmology provided mathematical frameworks suggesting that extreme densities might not lead to singularities but instead to a rebound. Over time, the Big Bounce gained traction as physicists searched for alternatives to singular beginnings, integrating insights from quantum physics, relativity, and cosmic geometry. The mechanism behind the Big Bounce relies on the idea that as the universe contracts, quantum effects or modifications to gravity prevent a total collapse. Instead of reaching an infinite density point, the universe reaches a smallest possible volume, then expands outward. Matter and energy compress during contraction, temperatures rise and structures degrade, but the bounce transitions these conditions into a renewed expansion that forms new cosmic structures. The long-term consequence of this model is a universe with no final destruction. Instead, each cycle ends in contraction followed by rebirth. While not the dominant cosmological model, the Big Bounce remains a compelling possibility, supported by certain quantum gravity interpretations. It continues to be explored as a potential explanation for the origin and future of the universe. Vacuum decay is a theoretical scenario in which the universe abruptly transitions from its current state, known as a false vacuum, to a lower energy true vacuum. This shift would fundamentally alter the laws of physics and dismantle all existing structures within moments. The theory is significant because it arises directly from quantum field theory and the behavior of the Higgs field, suggesting that the stability of the universe is not guaranteed. Instead of ending through gradual processes such as expansion or collapse, vacuum decay describes a sudden, unavoidable, and potentially instantaneous transformation that reshapes space-time itself. The idea emerged as physicists explored the implications of the Higgs mechanism in the 1970s and 1980s. As researchers studied the potential energy landscape of the Higgs field, they realized that the universe might not reside in the most stable possible state. This concept gained renewed attention after the Higgs boson's discovery in 2012, when its measured mass implied that the vacuum could be metastable. Over time, vacuum decay became a widely discussed theoretical outcome, connecting particle physics with cosmological questions about the universe's long-term fate. The mechanism behind vacuum decay involves the formation of a true vacuum bubble somewhere in the universe due to quantum fluctuations. Once created, this bubble expands at nearly the speed of light, erasing the existing physical laws within its path. Forces, particles, and even the structure of space-time are redefined by the lower energy state. No warning is possible, as the bubble would travel faster than information can propagate. If this process occurs, the universe ends not by collapse or fading, but by instantaneous transformation. Every structure, from galaxies to atoms, is overwritten by new physics. While vacuum decay remains theoretically possible, most models suggest the universe is stable for unimaginably long timescales. It remains an important scenario in discussions of quantum stability, Higgs field behavior, and the ultimate vulnerability of cosmic structure. The Big Slurp is a theoretical cosmological scenario closely related to vacuum decay, describing the sudden collapse of the universe into a lower energy vacuum state. It envisions a catastrophic event in which a bubble of true vacuum forms and expands, consuming the existing universe at nearly the speed of light. This theory is significant because it highlights the potential instability of the universe at the quantum level, suggesting that cosmic destruction could occur without warning, and that the current laws of physics may not be permanent. It underscores the delicate balance of fundamental forces and the long-term vulnerability of all cosmic structures. The concept of the Big Slurp developed from studies of the Higgs field and quantum field theory in the late 20th century. Physicists investigating the energy landscape of the vacuum realized that our universe may exist in a metastable state, not the absolute lowest energy configuration. With the discovery of the Higgs boson in 2012, models indicated that a transition to a lower energy vacuum, while extremely unlikely in the near term, is theoretically possible. The Big Slurp emerged as a vivid representation of this possibility, bridging particle physics and cosmology in discussions about the ultimate fate of the universe. The mechanism of the Big Slurp involves the spontaneous nucleation of a true vacuum bubble, triggered by quantum fluctuations. Once formed, the bubble grows at near light speed, overwriting existing spacetime, matter, and forces. Galaxies, stars, planets, and even subatomic particles are destroyed as the universe's physical constants shift to a new configuration. This process occurs without any preceding warning and leaves nothing recognizable behind. In its aftermath, the universe exists in a fundamentally altered state, dictated by the lower energy vacuum. While this outcome is largely speculative, it remains an important theoretical scenario, informing studies of quantum stability, Higgs field dynamics, and the ultimate fate of cosmic structure. The Proton Decay end, also referred to as the degenerate era dissolution, is a theoretical scenario describing the universe's fate billions of years into the future. It proposes that, over immense timescales, protons, the building blocks of ordinary matter, will spontaneously decay, leading to the gradual disintegration of all atomic structures. This theory is significant because it provides a framework for understanding how matter itself may ultimately vanish, marking the transition from a universe filled with stars and galaxies to one dominated by diffuse radiation and elementary particles. It highlights the long-term consequences of particle physics on cosmology and the eventual entropy-driven evolution of the cosmos. The concept emerged in the mid-20th century as particle physicists considered extensions of the standard model predicting proton decay. Theoretical work by scientists investigating grand unified theories suggested that protons are not absolutely stable but have extremely long lifetimes, potentially exceeding 10 to the 34th power years. These studies connected fundamental particle behavior with the large-scale structure of the universe, creating a model in which the gradual breakdown of matter defines the universe's final stages. Over decades, this idea became central to discussions of the degenerate era and the ultimate dissolution of structures formed from ordinary matter. The mechanism relies on the spontaneous decay of protons into lighter subatomic particles, such as positrons and neutral mesons. As stars have long burned out and black holes gradually evaporate, remaining matter continues to disintegrate. With the slow loss of protons, planets, stellar remnants, and interstellar matter dissolve, leaving an increasingly sparse universe dominated by photons, neutrinos, and electrons. The process is gradual but inevitable over immense timescales. Ultimately, the universe reaches a nearly featureless state, devoid of stable matter, with only low-energy particles and radiation remaining. While the theory remains speculative due to the unobserved nature of proton decay, it is widely considered in cosmology as a plausible outcome, illustrating the profound connection between particle physics and the long-term fate of the universe. The cyclic universe is a cosmological theory proposing that the universe undergoes endless cycles of expansion and contraction, avoiding a definitive beginning or end. According to this model, each phase of expansion eventually halts and reverses, leading to a contraction or crunch, followed by a rebound or bounce that initiates a new expansion. This theory is significant because it provides a framework for a self-renewing universe, addressing questions about the origin and fate of cosmic structures while avoiding singularities and ultimate heat death. It presents an alternative to one-time scenarios, such as the Big Crunch or heat death, emphasizing continuity and regeneration. The origins of the cyclic universe concept trace back to early 20th century considerations of oscillating universes, particularly the work of Richard Tolman. These initial ideas explored the implications of a universe dominated by gravity that might reverse its expansion. In recent decades, the theory has been refined through developments in string theory, brane cosmology, and loop quantum gravity, which provide mechanisms for avoiding singularities and ensuring rebirth after contraction. Modern versions of the model integrate both quantum effects and dark energy considerations, making the cyclic universe a compelling alternative within theoretical cosmology. The mechanism involves alternating phases of cosmic expansion and contraction. During expansion, galaxies, stars, and cosmic structures evolve normally. Once expansion slows, gravitational forces dominate, and the universe begins contracting. Matter and radiation become compressed, temperatures rise, and large-scale structures merge. Near the minimum size, quantum gravitational effects or high-energy physics prevent a singularity, triggering a bounce that initiates a new expansion phase. Each cycle is followed by another, continuing indefinitely. In the long term, the cyclic universe predicts a universe that never truly ends, with each cycle resetting cosmic conditions while retaining certain large-scale features. While the model is highly theoretical and faces challenges regarding entropy accumulation and observational verification, it remains a prominent concept in discussions of eternal cosmology and the ultimate fate of the universe. The black hole era. Fade-out is a theoretical stage in the universe's far future evolution, following the exhaustion of stars and the decay of ordinary matter. It envisions a cosmos dominated almost entirely by black holes, which themselves gradually evaporate via Hawking radiation over incredibly long timescales. This theory is significant because it describes a universe where even the most stable and massive structures eventually dissolve, marking a transition from the degenerate era to a near-empty cosmos. It highlights the ultimate influence of quantum effects on gravity and the long-term fate of all astrophysical objects. The idea emerged in the latter half of the 20th century as physicists explored the implications of black hole thermodynamics and Hawking radiation. Stephen Hawking's discovery that black holes can emit radiation and slowly lose mass provided the foundation for this scenario. Cosmologists combine this insight with predictions about stellar evolution, proton decay, and the gradual dimming of galactic activity, creating a coherent model for the black hole era and its eventual fade-out. The mechanism involves black holes slowly losing mass through Hawking radiation. Over timescales far exceeding the current age of the universe, even supermassive black holes will evaporate entirely. As black holes disappear, any remaining matter and radiation disperse, leaving a sparsely populated universe with extremely low energy density. Temperature continues to approach absolute zero, and interactions between particles become increasingly rare. In the long term, the universe reaches a near-total state of emptiness, with only diffuse photons, neutrinos, and elementary particles remaining. No large-scale structures persist, and the cosmos is dominated by cold, low-energy remnants. While largely speculative due to the extreme timescales involved, the black hole era fade-out remains a key theoretical endpoint in cosmology, illustrating the ultimate consequences of entropy, Hawking radiation, and the inexorable passage of cosmic time. The Big Change is a theoretical cosmological scenario in which the fundamental laws of physics could abruptly and randomly alter, reshaping the universe in unpredictable ways. Unlike gradual endpoints such as heat death or the Big Rip, this model envisions a sudden upheaval in the constants and forces that govern matter, energy, and spacetime. Its significance lies in highlighting the fragile balance underlying the cosmos, suggesting that the stability of all structures, from atoms to galaxies, depends on the continued constancy of physical laws. The Big Change represents a radical form of cosmic evolution, challenging the assumption that natural laws are immutable over time. The idea originates from speculative research in quantum cosmology and multiverse theory, particularly studies exploring metastable vacuum states and variable fundamental constants. Discussions by theoretical physicists over the late 20th and early 21st centuries, including considerations of string theory landscapes, have examined the possibility that local physical laws could shift due to quantum fluctuations or transitions to alternative vacuum configurations. Over time, this concept has become a recognized, though highly hypothetical, scenario for the universe's fate, connecting cosmology with fundamental particle physics. The mechanism involves spontaneous alterations in constants, such as the gravitational constant, the speed of light, or the strengths of electromagnetic and nuclear forces. Such a shift could disrupt atomic bonds, destabilize planetary systems, and unbind galaxies, fundamentally altering the behavior of matter and energy. This process could occur nearly instantaneously across the cosmos, leaving existing structures unable to survive under the new laws. Ultimately, the Big Change could render the universe unrecognizable, with traditional matter ceasing to exist and spacetime itself potentially reconfigured. While no empirical evidence currently supports this scenario, it remains an important theoretical consideration in cosmology, emphasizing the precariousness of the universe's long-term stability and the uncertainties inherent in predicting its ultimate fate. Dark energy reversal is a cosmological theory proposing that the currently observed accelerated expansion of the universe could eventually slow, halt, and reverse, leading to a global collapse. Unlike models predicting eternal expansion or gradual decay, this scenario envisions a universe in which dark energy, the mysterious force driving cosmic acceleration, changes behavior or diminishes, allowing gravity to dominate. The significance of this theory lies in its potential to explain a universe that ends in contraction rather than indefinite expansion, offering a plausible alternative to heat death or the Big Rip. The concept emerged after the discovery of cosmic acceleration in the late 1990s, which highlighted the role of dark energy in shaping the universe's long-term evolution. Theoretical physicists and cosmologists began considering the possibility that dark energy might not be a constant, but a dynamic component capable of weakening over time. Early contributions by researchers in the fields of relativistic cosmology and dynamical dark energy models laid the foundation for this reversal hypothesis, integrating ideas about vacuum energy and scalar fields into the evolution of the cosmos. The mechanism involves a gradual reduction in dark energy's repulsive effect, allowing gravitational attraction to regain dominance. As the expansion slows, galaxies draw closer, stars merge, and large-scale structures begin to collapse. Over immense timescales, matter coalesces, temperatures rise, and the density of the universe increases. Eventually, all cosmic structures converge toward a singular, highly compact state, similar in density and temperature to the early universe. The ultimate outcome is a complete contraction of the universe, resulting in a final, extremely dense state that may lead to a singularity. While this scenario remains speculative, it is considered theoretically plausible within models of variable dark energy. It provides an important alternative framework for understanding cosmic evolution, demonstrating that the universe's long-term fate is intimately linked to the behavior of dark energy and gravitational dynamics. The quantum decay of spacetime is a highly speculative cosmological theory, suggesting that the very fabric of spacetime could become unstable and spontaneously disintegrate at some point in the distant future. Unlike other end-of-universe scenarios, which involve the decay or collapse of matter and energy, this model envisions the breakdown of the underlying structure that supports the universe itself. Its significance lies in the radical implications for physics and cosmology, as the disintegration of spacetime would render all conventional notions of space, time, and causality meaningless. This scenario highlights the extreme possibilities allowed by quantum mechanics and theories of quantum gravity. The concept emerged from studies in quantum gravity and theoretical physics during the late 20th and early 21st centuries. Physicists exploring the unification of general relativity and quantum mechanics consider that spacetime may not be fundamentally continuous, but instead susceptible to quantum instabilities at extreme scales. Discussions around vacuum fluctuations, Planck scale phenomena, and the limits of spacetime smoothness provided the basis for this hypothesis. While largely theoretical, it is increasingly considered in models addressing the ultimate limits of physical law. The mechanism involves the spontaneous destabilization of spacetime due to quantum fluctuations or tunneling effects. As the universe evolves, local regions of spacetime could collapse, merge, or vanish entirely, propagating instability throughout the cosmos. Conventional matter, radiation, and even the concept of distance and duration cease to exist as the fundamental stage on which physics operates disappears. In the long term, the universe would reach a state beyond conventional comprehension, with no spatial or temporal reference points remaining. All structures, forces, and particles would lose their meaning, resulting in the total cessation of the observable universe. While the theory is purely speculative and cannot be tested with current technology, it remains a profound consideration in theoretical cosmology, illustrating the ultimate uncertainties in predicting the universe's final fate. Thank you for watching this video. If you enjoyed, please leave a like and subscribe and let me know in the comments if you would like to see more videos like this one. Thanks again. Goodbye.